Okay, the last topic in chapter 20, the last major topic with calculations is mass to energy conversions. And this is using Einstein's famous equation of E equals mc squared. So essentially for the very small particles, there is energy that is associated with mass, and mass is associated with energy. And for these nuclear reactions, mass and energy are, they convert between one another. So for this equation, delta E, we're going to use the delta here for a change, is in joules, and it's always positive because it's the energy that's released from these nuclear reactions. The negative sign is just by convention. The delta M is the mass defect. It's in kilograms, and it's basically when two things combine together, they essentially annihilate one another, and the mass disappears and it's turned into energy. So that mass loss is a negative number. Negative sign here makes it a positive energy. And then the speed of light is just a constant. So this is known as the binding energy for a nucleus. Okay, and we'll explain what that is here in a moment. So binding energy per nucleon is, each nucleus is made up of a different number of nucleons. The nucleons are the protons and the neutrons. It's the A number. And when we calculate the binding energy, the total energy that's holding the nucleus together, we can divide it by the total number of nucleons, delta E over A, and this normalizes it to nuclear stability, so we can determine nuclear stability for different size elements. Okay, so that delta M up here allows us to calculate the delta E. So that's really what we're going to do, is be calculating delta M, and then we can calculate delta E. So to find delta M, mass defect calculations, the formation of the nucleus of deuterium, this is the heavy isotope of hydrogen, this is formed from combining of one proton and one neutron to make a deuterium, and it gives off energy. So we can calculate this energy by looking at the difference in masses between the products and the reactants. The delta M is defined as the mass of the products minus the mass of the reactants. And the mass of the deuterium nucleus with no electrons is here, minus the mass of the proton, which is a reactant, minus the mass of the neutron, which is also a reactant. And the reactants weigh more than the product. So the delta M is going to be negative, resulting in a positive delta E. So let's throw some numbers in here. Actually, we're going to look at a different problem. And this one says calculate the binding energy of the helium-4 nucleus. And where they're given the atomic mass of helium. And note that this does contain the electrons. So we have to account for that, because we're just looking at changes in mass of the nucleus itself and not including the electrons. So in that helium atom, there are 2 neutrons and 2 protons in the nucleus, and there's 2 electrons in the outside. The whole thing has a mass of 4.00260 AMU, and the masses of each of the subatomic particles are shown here: the proton, the neutron, and the electron. So in this binding energy reaction, to make this nucleus, we're going to need 2 protons, and we need 2 neutrons, and that's going to make the helium-4 nucleus, or that nuclide with no electrons. But if we're given the mass of the helium atom, we have to subtract the mass of the electrons. So the mass of that nuclide is the mass of the whole atom minus the 2 electrons right here. And that gives us 4.0015, which is the nuclide mass. Now we can use that in our delta M equation. As you can see, the mass of that nuclide is the product, and the reactants are the 2 protons and the 2 neutrons, just like we have up here. Okay, goes backwards. And so you got the mass of the nuclide, 4.0015, minus 2 protons, minus 2 neutrons, and gives us a mass defect of minus 0.03038 AMU. And it's always negative for binding energy. Okay, so we put that into the delta E equals delta MC squared equation with the negative sign, and we have to convert from AMU to kilograms in order to get delta E in joules. So we take that AMU number, that mass defect, and we multiply by this conversion factor, 1.66 times 10 to the minus 7th kilograms per AMU, and then times the speed of light squared. And that gives us a value of 4.54 times 10 to the minus 12th, which we call the binding energy for the helium-4 nucleus. Okay, now by calculating binding energy for nucleon, per nucleon, we can compare the binding energy per nucleon for different elements. And so for helium, it's that binding energy divided by the number of nucleons, which is 4, 2 protons and 2 neutrons, gives us 1.13 times 10 to the minus 12 joules per nucleon.